Level 2020, Paper 2. First question, A1, Part 3. Which substance other than iron is used in the manufacture of steel? Now, if you run through the option, cannot be hydrogen. Iron is really in the question. Graphite, no. Ethanol, no. Calcium hydroxide, no. Copper, no. And argon. So the answer is actually argon. Now, why is argon used in the manufacture of steel? Is argon is mainly and you should know that argon is a noble gas. It is unreactive. Now, why is argon used in the manufacture of steel? Is because argon is used as a shielding gas. Now, what is a shielding gas? Okay, shielding gas. And basically, it is used as a shielding gas to prevent oxidation of the steel. Because in the manufacture of steel, iron need to be melted first. So it is in a very, very high temperature environment. And all of you should know that in a high temperature environment, the steel as well as the iron could be oxidized by the oxygen in the air to form oxide. Yeah, that is why you need a inert environment, which argon can provide to prevent the oxidation of the steel. So argon is used as a shielding gas in this context. Second question, part 4. Okay, which substance is commonly used as a solvent? Yeah, solvent. Usually solvent is a liquid. It is used to dissolve chemical. Okay, so in this case would be ethanol. So commonly ethanol and water are the common solvent. So for example, some hand sanitizer, there is ethanol inside. So ethanol is mainly used as a solvent to dissolve the chemical used to make hand sanitizer. Another example would be some cosmetic products, which water and ethanol are commonly used. Next question, A2. So under room condition, nitrogen gas and oxygen gas do not react together in the atmosphere. But under conditions in a car engine, nitrogen gas reacts with oxygen gas to produce nitrogen oxide. So you need to know the difference between these two contexts is car engine, the temperature is very, very high. So which means that at temperature is very high, nitrogen and oxygen are able to react to form nitrogen monoxide. Now, use ideas about energy and collisions. So what is what are the keywords here? Energy and collisions. Yeah, so the keywords are basically activation energy. So from the second page of the speed of reaction mind map, you should know this part. The activation energy is the minimum amount of energy that reactant particles must possess in order for the chemical reaction to occur and for the products to be formed. So which means that in this case, the first key point, the first marking point would be under normal condition. Okay, under normal condition. Okay, under normal condition, nitrogen and oxygen, the collision between nitrogen and oxygen doesn't possess energy equal or greater than the activation energy. Yeah, and because of that, there is no effective collision. So no effective collision occur. So no product is formed. So in the car engine, the temperature is very high. So you need to know that temperature is high in car engine. And as a result of that, the collision between nitrogen and oxygen possess energy equal or more than the activation energy, more than the EA. Okay. Yeah, and because of that, there is a effective collision. There is effective collision, and hence NO is formed. So these are the key points for A2A. Next question, A4. Okay, so in this case, you need to explain. Food cans were made from iron, so a thin layer of tin metal was electroplated onto the can. So this is actually electroplating. So describe the setup that could be used to electroplate a layer of tin on an iron can. So you need to explain which is the cathode, which is the anode, what are the objects on the cathode, what are the objects on the anode, as well as the electrolyte used. So this is actually very similar to the electrolysis mind map, this part. So first thing, you need to electroplate an object with tin, right? So the object to be electroplated must be connected to the negative terminal of the battery. which is the cathode. And the plating metal, the tin, would be on the anode, would be connected to the positive terminal of the battery. And not forgetting the electrolyte is a salt solution of the plating metal. So in this case, the plating metal is tin, salt solution that contains tin, for example, tin nitrate. So that would be the answer for A4A. A6. When sodium is heated in a stream of hydrogen, sodium hydride, NaH. Okay, this is sodium hydrides, NaH is formed. So other group 1 metals react with hydrogen in a similar way. So this is the data, the table 6.1, group 1 metal lithium theoretical mass of metal hydride produced per gram of hydrogen. Okay, then for part B, the student make these statements about the results. Okay, Jean, Beth, and Ryan. Now, the amount of metal hydride. So amount, remember the amount of chemical actually refers to the mole. Mole is a measure of, is the SI unit or the measure of the amount of chemical. So this data here, we can do a bit of analysis. We can actually find out the MR. So MR for lithium hydride. So lithium hydride, which is LiH. Okay, because sodium hydride is NaH, right? So lithium hydride would be LiH. And the MR is 7 plus 1, which is 8. Okay, 7 plus 1, which is 8. And you can actually calculate the number of mole, which is mass divided by the MR, and you should get 1 mole. Now, so likewise for sodium, NaH. So the MR is 23 plus 1, which is 24. And the number of mole is 24 divided by 24, which is 1. And for potassium, similarly, KH. So the MR is 39 plus 1, which is 40. And then 40 over 40 is 1 mole. So you can see the number of mole are the same, all 1 mole. So let's take a look at what Jean said. The amount of metal hydride made from 1 gram of hydrogen increases down the group. It doesn't increase. In fact, they are all the same. For Beth, the amount of metal hydride made from 1 gram of hydrogen is the same for every metal. Yes, this is correct. And then for Ryan, the mass of metal hydride increases by exactly the same amount down the group. It doesn't increase, in fact. And then I predict that if rubidium is used, 56 gram of rubidium hydride. So rubidium, the AR is 85. So similarly, RBH. So you have 85 plus 1, there'll be 86. And then the number of mole, and then it says that 56 gram. Yeah, actually should be 86 gram. 86 gram of rubidium hydride will be made per gram of hydrogen, not 56. So that basically explain part 1. I mean the B part 1. Does the information support the statements made by Jean and Beth? And do you agree with Ryan's statement? Explain your answer. Okay, let's look at 7A. Okay, 7A is about de-icer. So use the data to estimate the number of moles of sodium chloride that dissolve in 1 dm cube of water. So in this table 7A, okay, let's take a look at 7A. Scientists wanted to find out if mixtures containing a higher mass of de-icer have lower freezing points. She made solutions by adding different masses of sodium chloride to 100 cm cube samples of water at room temperature. She then measured the freezing point of each solution. Okay, so you can see that for sodium chloride, okay, the mass of sodium chloride 30 grams, and then 40 grams does not fully dissolve, which means that for sodium chloride, you can only dissolve 30 grams in 100 cm cube of water at room condition. So back to the question, use the data to estimate the number of mole. So first thing is 30 grams of sodium chloride can be dissolved in 100 cm cube of water at room temperature. So what would be the mass that can dissolve, the mass of sodium chloride that can dissolve in 1 dm cube. So 1 dm cube is 1000 cm cube. So mass of NaCl that dissolve in 1 dm cube of water is 30 times 10, which is 300 grams. Okay, the question wants mole. So you have to convert it to mole. So the mole of NaCl would be 300 divided by the MR for NaCl, which is 23 plus 35.5, and that would give you 5.13 mole 3SF. That's 7A. Let's look at 7C. Some of the deicers are effective at much lower temperatures than others. Identify two factors that determine which deicers are more effective at low temperatures. So let's look at the different deicer at low temperatures. So over here, so you can see some deicer dissolve exothermically. So these are the deicer at low temperatures. Okay, these are the these are the deicer, low temperatures. All right. So some of them they dissolve exothermically, especially these two, which means that when they dissolve into the water, they gives out heat. Okay. So this helps to melt the solid ice under the layer of water and allows the deicer to work deeper in the ice. So the fact that some of the deicer dissolve exothermically would help to dissolve more solid ice. And then another factors is at low temperature, you can see at a very cold conditions, there might be very liquid water for the deicer to dissolve in. So for the deicer to be able to do its work, it needs to dissolve in the water. It needs water. But at very low temperatures, there might not be water available because all of them have already formed, all the water has already formed ice. So some deicer, they have this ability to attract water vapor from the air and use this to form a solution on the surface of the ice. And this is actually called hygroscopic. So especially these two. So these two deicer uh, dissolve exothermically in the water. Also, they can attract water vapor from the air so that the deicer can dissolve on the surface of the ice. So these are the two factors. This is B8. So which data in the table best supports the statement X, Y, and Z are isomers? So first of all, you need to know what are isomers. Isomers have the same molecular formula but different structural formula. So which statement actually supports that X, Y, and Z have the same molecular formula? Okay, it is actually the empirical formula because molecular formula is a multiple of empirical formula. Yeah, so if the empirical formula is the same and the MR are the same, it means that the molecular formula must be the same. So the data that best supports the statement that all three of these isomers are empirical formula and the MR. Again, if the empirical formulas are the same and the MR are the same, it means that the molecular formula must be the same. Let's look at B. Use the information in the table to deduce and draw the structural formula for each isomer. Identify the functional group present in each isomer. So let's look at X. So X, the information given, one CH3. So this is actually CH3. This is CH3. This is CH2. Okay, and this is the functional group COO. So now it doesn't mean that, for example, for Y, right, it has two CH3. It doesn't mean that these two CH3 are next to each other. So this is something that you have to bear in mind. Also, some information is missing because if you look at it for X, right, it has one CH3, that means one carbon, two CH2, that means two carbon, and then one COO, that means one carbon. So total 1, 2, 1. So there are 4 carbon atoms. But for Y, there are only 3. And for Z is 4. So some information is missing. So it doesn't mean that the structure must contain exactly 121 or 201. Because for example, for Y, one of the carbon atom is missing. It is not given in this table. So this is something that you have to bear in mind. So for X, it's very simple. You have, it has CH3, all right, CH3, and then it has 2 CH2, and then it has C double bond O, single bond O. And of course, each oxygen atom must share 2 pairs of electrons. So something is missing here. One more line here. And this one is a hydrogen. Because COOH, that's a carboxyl group. So this is the isomer X, and the functional group would be the carboxyl group, which is COOH, this one. Okay, let's look at the second Y isomer. So it has 2 CH3, no CH2, and 1 COO. Okay, 2 CH3. Okay, let's draw it here. So 2 CH3, right? Now it cannot be like this. It cannot be like this. Because if it is like this, right, then how are you going to draw the C double bond O single bond O? You know, it doesn't make sense, because your hydrogen only share one pair of electrons, cannot share two pairs. Okay, so for this one, it's CH3, right? Okay, then it must join with another carbon and then another CH3. Yeah, then after that, join with the COO, C double bond O, single bond O, and then one more H. So this would be the structure for this isomer. So you need to innovate. You need to think out of the box. Yeah, cannot draw the hydrogen here. Yeah, you have to think out of the box where to put the CH3. Okay, so this carbon, is it correct? It is not, because each carbon atom must share 4 pairs of electrons. So there must be one more pair here, and this would be the hydrogen. So in this manner, all the carbon atoms share 4 pairs of electrons each. Okay, how about the functional group? The functional group is COO. Yeah, so the functional group, same thing, COOH, which is the carboxyl group. So that's for isomer Y. Okay, let's look at isomer Z. It has 2 CH3, 1 CH2, and 1 COO. Okay, again, 2, 1, 1. Okay, so this one. So 2, right? 2 of this, 2 CH3. But the 2 CH3 cannot be drawn next to each other. So how about 1 CH2? Okay, then straight away I join the COO. Okay, join the COO. I have one more CH3. So join here, CH3, just nice. Yeah, so this would be another isomer. And in this case, the functional group would be the COO. And the COO is the ester linkage.